Ok.
Poi si dice 5 ore avanti adesso perché non è ancora cambiata l'ora lì.
Sì, sono le 2.
Ah, ok. Okay, hello again. Let's continue to solve for the control vector. So again, we got to this form q eta equals to something that has the dimension of a torque and includes also the external torques, and if you want, the minus b gamma double dot term, if you don't want to neglect it. And remember that we got here by substituting the expression that comes from the Lyapunov function for the omega error. So what I'm trying to do here is define find a solution that will satisfy this equation, because that's the one that we want to satisfy with the Lyapunov theory. And at the same time, since we have in principle more variables than equations, we have 3 equations here, we are going to have usually more than 3 variables, control variables. Well, we have the freedom to set up the problem in different ways, and so the one that I'm choosing that you will implement for your simulation is the minimum solution for eta constrained, with the constraint being the equation of motion according to the Lyapunov theories. So okay, so basically the problem that I want to define, and let's refresh for a second the weights in this matrix. The WGs are, these are all scalars. These are the weights for the gimbals, can be chosen to be some values that we keep constant, while we're suggesting to weigh more the use of the wheels, so in case they can actually spin up or down as a function of how close we are to being singular. In other words, how close this delta is to 0. As you can see, you get the maximum of this exponential where delta is 0. Okay. So the problem to solve is, let's say that we define some kind of cost function. I call it h of eta, and that represents the magnitude of the controls through the weights, though. So we're setting up as 1/2 eta transpose, so it's a row vector, multiplies the inverse of W, the weight matrix, times eta. For conveniency, we'll see why. So the problem to solve, it's minimize h excuse me, and at the same time remain constrained. Okay, so this is the constraint. So, well, this kind of problem can be solved introducing what we call Lagrangian multipliers. It's 3 of them, really, because, these are 3 equations. Let's call the Lagrangian multiply vector as lambda 1, 2, and 3. So we can solve the problem by creating an augmented function, which is some f built this way. We have the one to minimize, and then the Lagrangian multiplier that multiplies the constraint. Call this M momentum exchange device. Okay. So the bottom line is that we want to basically impose that the partial of f with respect to this would be a partial. With respect to eta has to be 0, and at the same time the partial of f with respect to lambda has to be 0, and this is just a constraint equation again, right? So the first one, the partial of f with respect to eta, is giving me W inverse eta itself plus Q transpose lambda. All I'm doing here is I would get lambda transpose Q, I just transpose both and change the order, so that's what I get, and this is equal to 0. And obviously the second equation, as we said, it's giving me the constraint again, just in this form. MED equals 0. From the first equation, so from this one, we will get that the vector eta is minus W Q transpose lambda. So we're almost finding the solution. This is a known matrix that I define. The Q is, well, the assembly of D and C, and so we need to find lambda here. So what do we do? Well, we have, let's see, we have, well, substituting. So we combine this equation with this one here, the constraint, and we get substituting eta. So basically we take this eta expression, we plug it in the constraint equation, we get minus Q W Q transpose lambda minus the MED equals 0, and so we can solve for lambda as minus Q W Q transpose all inverse MED. So finally, we find an expression for the control. Control vector can be given as W Q transpose Q W Q transpose inverse MED. And here is your final feedback law that has come from the dynamics with the momentum exchange devices being calculated on the Lyapunov function that I've introduced, and trying to minimize the control effort, so the magnitude of the eta vector, according to the problem that we just solved. So what happens here is that basically, well, when the theta goes down, we prefer, if you like, the use of the gamma dots to compensate for the CMGs being less and less capable of giving the torque that you want. So this is in general for variable speed quantum moment gyros. Now the other thing that you want to do, that you may want to do, is you can simulate CMGs. Can be represented or simulated. How? Well, you choose very high mu values in the weights. What that means is you try to avoid using the capital omega dots, because those are the CMGs. You want to lock the wheels at a fixed rate, and so the weights that we have chosen, when I start selecting very high values of mu's, you know, extreme case to infinity, these will go to 0, and so the weights for the wheels will be very small and not not preferred. And as you can see here, the way, aside from these Q transpose Q, etc., the W matrix appears in the expression for eta. So if you start reducing the diagonal, the part of the diagonal that is corresponding to the omega dots, well, those omega dots will be very small up to the point of being 0 if your mu is infinity, you know, just to exaggerate. But basically, that's the way for you to limit the use of the wheels. If you want to simulate reaction wheels, can be simulated basically doing this. Inverting, you can do this, inverting the weights in the W matrix and selecting again a high mu. So in other words, you do the same thing that I've just mentioned, except now you want to have small weights for the gimbal components so that the gamma dots are pretty much 0. You lock them in place. So you can do it in many different ways. I mean, the choice of calling the weights for S as function of delta for the reaction wheels, you can basically throw that away and just say that these weights are, the gimbal weights are 0 pretty much, and so you only retain the weights for the wheels, what we call WSs, but we keep them constant. We just choose some values for them because that's you know, that's what we want to use. Okay. So is what we've done today making any sense for all of you? I think we can stop theory for today, and we have a couple of hours, or well, at this point a little less, but we can start working on this assignment, or we can finish the gravity gradient first. Maybe that's what we can do for the remaining portion of this hour. Is the gentleman who started the gravity gradient here now? No.
Yeah, I mean.
Oh yeah. Hi. Did you have a chance to keep working on that?
Yeah, no problem.
No, I mean, did you have time to make any modifications compared to yesterday?
Okay, sorry, I didn't send. No, actually.
Okay.
But
let's work on that. Cool. Okay, so Mr. Grasso is going to share the screen again, and we'll do that for the next 45 minutes, and then I think we'll probably be tired enough of being the one. I'm really hoping that another gentleman, since we had 2 ladies already, will start from scratch working on the homework too. The first thing to do would be putting together the blocks that simulate the wheels and the assemblies, the initialized file that I shared with you. In the meantime, Mr. Grasso, you can share your screen, of course.
Yeah.
The initialized file that I gave you is intended to have 3 variable speed control moment gyros, and the initial orientation for them is already given as the G, S, and T vectors, so that should be easy to do. Okay. Any questions?
Okay,
we start playing with this on the variable speed control moment gyros, the equations for the MEDs, the way we derive the control law. Was everything pretty much clear, despite maybe skipping some steps here and there?
Yeah, more or less, especially for the all the passages. But
more or less meaning, is there any part that I can clarify, or?
No, to me it's mainly a problem related to passages that maybe I lost something, but I think that the main points, I got the main points.
Okay. So also what I did today is in my notes that I posted in the folder for the first time we met, and also for today. There's a few more pages on those notes. If we have time, we can go back, and I use the same approach, identical approach, Lyapunov theory, to derive a much simpler set of equations that would be for external torques. So non-momentum exchange devices, thrusters, for example. So I have some calculations for that and also an example to show eventually. But let's keep going with these. I think we had a very useful comment yesterday about having to initialize the problem aligned or very close to LVLH. And I don't know if that was working.
Actually, me and my colleague Alessia Nocerino, that is here now, we have already implemented some preliminary blocks and equations about the next problem. So maybe for now it's better that I comment out all these blocks. I don't know if then we can continue maybe with the help of Alessia.
Okay.
So for now we have to concentrate with this problem. That is I have these results.
Change the initial condition to come from somewhere else, right?
Yeah. Initial condition now are this Q0.
Okay.
That comes from here.
It should be the DCM of the LVLH.
The LVLH, yeah.
Yes.
That goes to the other blocks, the rigid dynamic block. And maybe it's here that there is a problem.
Well, so let me think. The definition of quaternion, and thanks for finding that was my swap had a typo. The definition of quaternion that I've been using as the scalar part as the last one. So this DCM block to quaternion is probably outputting something different. So yeah.
So
we need
from this block we have the right quaternion with the scalar part at fourth component. Did we
do it inside?
Yeah.
Okay.
If I remember, yeah. Yeah.
But that's not how we should do it, right? Is it? I think that was my error, wasn't it? Because let's see. It's true that maybe you need to see my overhead camera here. So if it's true that that block, as one of your colleagues verified, is outputting these, is outputting Q scalar, let's call it that way, and then Q1, 2, and 3. So this is 1, 2, 3, 4. Then the corrected quaternion, Q correct, let's call it that way, should be Q1 here, right? This has to go here. And then you shift everything. So this should be Q2, Q3, Q4. So I think we need to fix that.
Okay.
No? Yeah, I had the same error in my code. Still pretty surprised that I didn't catch this, and I'm wondering whether there was a reason for me to do so, but
okay, so
yes,
2,
3, 4.
3, 4.
Yes, and then 1.
And 1. Okay.
And then, is there any other place where we convert from DCM to Q? That's the only one, right? Oh, wow.
I think that's these must be put here.
Oh, yeah. And then there was also a comment whether we are using the correct DCM between spacecraft and
this matrix.
yes.
Are
Well,
you asking if this is correct?
well, if the output of all that, no, that's the form of that is fine. Whether we need to transpose that, you know, why? Well, what do we get? I'm trying to remember what we're doing. What do we get? Okay, the one on top, basically. The one on top is the output of that would be the DCM between spacecraft and LVLH. And so I'm wondering if that needs a transpose or not. That's what I'm saying.
Okay, we
want to see what I have.
These.
Oh.
Are you wondering if this block is right transposing the
No,
matrix?
that's probably fine. The end of everything after the matrix multiply. I'm just wondering if we're really outputting the DCM that goes from spacecraft to LVLH, or actually the opposite, LVLH to spacecraft. Because the way I have defined the DCM for my calculations, where the axis of LVLH are transformed, are obtained. Oops, no. I started from this. I said the B axis are obtained as C11, C12, C13, etc.
Okay.
Applied to A1, A2, and A3. And I have called these the C that goes from A to B, right? So it goes from LVLH to spacecraft. So I have the feeling that what we output out of that matrix, that we may be doing something incorrect. So we need to think about this a little careful. And it's just a matter of transposing some matrix. Really.
Yes.
But I need to be sure that we're doing the right one. So, and so the way we're saying that we want to assemble the CBA basically is by multiplying first the C that goes, basically it's the rotation matrix that goes from A to inertial, right?
Okay.
And then in front of that we have the rotation matrix that go from inertial to spacecraft. Correct?
Here inertial is LVLH. Yeah. Are you meaning LVLH? Because we have LVLH. Correct.
Yeah, the LVLH is what I'm calling A here, but yeah.
Okay.
And so this matrix that goes from A to N is coming out of there. And that's so what I'm asking is that DCM that goes from LVLH to inertial, or vice versa? That's the first question to ask.
DCM is it goes from inertial to LVLH, right?
Be careful.
Yes, I agree with you.
Yeah.
So, I'm sorry, from LVLH to inertial. Okay. No, you said from inertial to LVLH. Correct? So we need to transpose that. So to obtain this, we need to transpose that. Agree?
Yeah, I had problems with the connection. I lost the last words. You said what you said.
No. So what I was asking is if the DCM that we are creating out of that function is the DCM that goes from LVLH to inertial or inertial to LVLH?
I think that it's from inertial to LVLH. Right?
Then we need to transpose it, which we are doing, right? To obtain this one. And so we're doing that.
Yeah.
Okay.
And we are doing that. Yeah.
Okay. And then this is the other question.
Here from Okay, just to recap. Here we have the DCM from inertial to LVLH. Then this is transposed, so becomes from LVLH to inertial, that terms. That is multiplied. This one is inertial to spacecraft. Yeah, inertial to body.
And so the order of that multiplication is incorrect.
Ah, okay. Yeah.
I think, right?
Right.
And so my sanity check usually, I'll admit I'm really terrible with rotational matrices. I always make the mistake and I end up transposing.
Yeah.
So I'm telling you right away. But my check is usually, so if I want to make sure that this is what I'm obtaining here is the one that goes from A to N, what the DCM should do is it should allow me to get, say that I have a vector expressed in LVLH, some V vector expressed in A. It should allow me to take that vector, put the DCM in front of it, and it should give me the vector N.
Yeah.
So these are the checks that you guys may want to perform before you say, okay, this is the correct matrix or not, or I have to transpose it.
Okay.
So, but I think this makes a little more sense now. But again, this is a joint effort, so thanks for all the inputs. This is good. Now, if you run this, it should try to oscillate a little bit, but I'm sure it won't.
Yes. Now the initial condition what are, because yesterday we have changed something.
Oh.
What? Probably the J matrix. So
that's fine.
try with it's fine. Okay.
Yeah, I think exaggerating the effect is fine. It should
V0 that is to have a circular orbit.
Yeah.
This variable is the right one. Okay.
So.
And it is TF. Can I try with tolerance level?
Yeah.
Because
make it a little faster.
It's very slow. Yeah. Uh, 6 or
yeah.
Okay. Okay. Okay, no mistakes. Wonderful.
Still pretty slow, huh?
Yes, yeah.
I mean, you can relax that. Maybe it's not really that important. I don't know.
Try to change from 6 to 3, for example.
Yeah, I mean, you already have a pretty tiny time step anyways. Even the maximum time step may be a little too small now. I don't know.
Yeah.
Yeah.
Modeling. Auto.
I don't know. Try 0.1. Yeah, maybe 0.1.
0.1.
Yeah. I'm not a big fan of auto.
Okay. 3.
Yeah. Try.
Yeah. Better.
Yeah, I mean, if you think about it, there's a lot of non-linearities. The orientation is affecting the torque, which is the input. So.
A lot of calculation.
Yeah. How long is the orbital period? We can check. Anyways. The thing is also, this is a pretty high orbit. I think I gave you a high orbit, maybe it's a little too high. What is 8,000, 6,000? We can probably go lower.
10,000 seconds.
Okay. 10,000. Yeah, it's pretty high.
Yeah.
Um,
I spent Leo 5,000, 6,000
yes,
seconds.
yes. So we can probably also do that and put ourselves into.
We have half of the period.
Yeah, I think we should go to Leo and make it a little lower. Almost.
Okay.
Yeah.
Wow.
Yeah, I can't tell much about these plots, really. Definitely, I don't see much stability. And I do see a strange behavior. I mean, it's like it's changing over time. Okay. Well, let's do the next thing to go a little lower with the orbit. What is the magnitude of that initial vector that I gave you, R0? How high is it?
R0. 8,000, 6,000.
Let me see. I want to open my own MATLAB here. Hello? Still there?
Yeah. Okay.
Right. I lost you for a second. I don't know why.
Yeah.
Okay,
Okay.
so
You asked me the R0. That is.
yeah, I can do it myself here real quick. Norm of R0, right? It's a 10,000, so it's a 4,000 kilometer orbit almost. Yeah, it's pretty high. Let's make it. What if we do half of that? 5,000. That's too small. R0 divided by. Yeah, it doesn't matter. Let's just you can take that R0 and just comment it out and give an initial position of, I don't know, 6,378 plus 400. Let's make the first component 6,800 kilometers, and then so that's X.
6,800.
Yeah. No. 6,800 for the first, and then actually I would put zeros on the other ones. So this is starting in some position on the equatorial plane, and then that should work. Yeah, let's try this. Is it running?
Yeah.
Okay. Okay. So, very nice. Yeah, I don't think it's stable. I'm debating. So the initial condition we give to the numerical integrator is that the way to do it? Is it really just giving it the initial one, or is it updating that initial condition every time step? That's something that I don't really know how it's done in Simulink. You know what I mean?
I don't think so. I can.
So
you mean something?
No. If you go back into there is a numerical integrator for the.
Okay.
Yeah, the one where we give an external initial condition. What is it?
Yeah. That is one.
So, because you're feeding something that comes from so that Q0 that is coming in, it's actually changing all the time, right?
Yeah.
So
each
is that
simulation step.
I'm sorry?
For each simulation step is changing.
Yes, and
Right.
I'm wondering what is that block doing? Is it using only the first one as initial condition, or is it just reusing it every time? You know what I mean?
Yeah.
I don't know what
check.
that. Let's see. External reset, none. I don't know. I have the feeling that it may be doing something weird.
So this initial condition is changing for each simulation step.
Yeah,
so
I don't. Yeah.
The initial condition is changing.
We should go into the help of this thing. Simulink.
Initial condition.
I don't know.
These resets, but I think that is our case.
It doesn't say. I'm looking at the same. I mean, it should not. You should use it once at the beginning, right? Only,
Yeah.
but I don't know if that's true.
Because it is calculated for each time step, so that change here. So we need only the first calculation of Q0.
Yeah. So I have the feeling that he may be actually changing that all the time.
Yeah, I think so. Standard set known. Rising for the
I mean, for the purpose of we can output the Q0 in this simulation and just you know, look at it and see what's the initial value. That would be a way.
Okay.
Maybe.
Yeah.
Go ahead.
But here we need the Q0, this Q0, because it is the desired Q0.
Yes.
Right. That can be different from 0001. That is
Yes.
a limited choice. Okay. So we now plot Q0. Okay, Q0. Let's check. Powering on.
I can't find much help online about what it really does with that initial condition input. That's weird.
This is the first call.
Really?
First calculation of Q0.
That's weird.
0, 1, 0.
Okay. And that's the in the correct. Yeah.
Here, memory is 0001.
Yeah. Okay, if that's the one, use that one. But that
0010.
hold on a second. So this Q0 that we're giving, hold on a second. This should be the okay, it's the initial quaternion for the I'm getting lost a little bit. This is the quaternion, the initial orientation of the spacecraft, and we want to make it so that it's aligned with the LVLH.
LVLH, yes, correct.
Okay. And so how are we doing that again? Where is this Q0 coming from? It doesn't seem like it's coming from the right block, is it?
Okay, it is coming from this block.
The side. Okay, the desired
is
was
this.
okay, that's fine. Yep, that's fine.
Okay.
So yeah, whatever is the initial value of the Q0, that should work as the initial condition for the spacecraft.
Okay, so I put here a constant. Which is 0, 0, 1, 0.
Yeah, and given the initial condition I gave you, I'm wondering if that makes sense, because basically the initial condition I gave you in ECI is a satellite that is here on the x-axis of ECI, and so the A3 is pointing like this way. The velocity was on the Y component, if I'm not mistaken. Can you go to the initial condition? Initialize. I think it was a positive Y, right? Yeah. So the velocity is this way, and in this case, it's a circular orbit, so A1, and then so the orbit is flying that way, so A2 is this way. So you want your spacecraft to be oriented this way, and you're telling me that the initial quaternion corresponding to this is 0, 0, 1, 0?
1, 0. Yes.
So the last is the scalar one, and it's, how did we define this? Cosine theta over 2? Correct?
Yes.
That's our definition of quaternion.
Yeah.
I think so. And so being 0 means that theta is pi. Over 2. Correct?
Just wondering what this block actually is doing. Okay.
Yeah. Well,
just to see the equation, because
yeah, that I honestly, I'm using my own the function that I showed you that I probably stolen from this block like this. I don't remember. So if this is theta, then this is telling me pi level 5. Yeah. Okay. This is telling me that my the vector part of the quaternion is 0, 0, 1. This is the E axis. Correct? I think so. So, yeah. So my initial orientation corresponds to an Euler axis that has components 0, 0, 1. So it's like this. And the rotation is pi. Weird. Is it? If I rotate, so if my body initial axes are aligned with this, then I rotate about this axis pi. This means that this axis is going to point that way. This axis is going to point that way. I mean, I'm not convinced.
bit strange.
I'm not totally convinced. I'm just trying to visualize. I mean, doing it with quaternion is just pretty terrible, but if that is the initial quaternion of my rigid body in the inertial basis, and I know that my spacecraft is starting here.
Yeah.
No. Did we say? Yeah. The roll axis was in the velocity direction, right? The way we defined it?
Yeah.
Okay. So, yeah, my bad. The angular momentum is actually pointing down, so A2 is actually pointing up. Correct? Okay, because the velocity is in this direction. So, okay, this makes a little more sense, maybe. Maybe. Let's see. Not really. Gosh. So, let's see. We're saying that the initial orientation is this. We are here. The velocity is pointing this way. This is V0. R0 is this vector. So my initial quaternion is 0, 0, 1, 0. And I am assuming that this is in the order that we have defined, with the last one being the scalar part. The last part was cosine of theta over 2, and that's a 0. If the cosine of an angle is 0, that means it's pi over 2, so theta is pi. It can be pi, or it can be minus pi, it doesn't matter. That's what it is. Now, if that is true, and I look at these other ones, it cannot really work, right? Can it? Because what is the sine of pi over 2? That's 1. Right? Okay. So the only way to get 0, 0, 1, since these are unit vector, this is a unit vector multiplied by sine of pi over 2, is that basically the vector itself has to be 0, 0, 1. There is an option that this could be actually plus minus pi over 2, and so this could be plus minus pi, and this could be plus, so this could be plus minus, and so this is plus minus. In which case, the only other thing that I could do is have the rotation eigenaxis to be 0, 0, minus 1, but I don't think it makes any difference, because in one case the rotation axis is pointing down, but the angle is minus pi. In the other case, it's pointing up and the angle is pi. So what I'm trying to understand is whether an orientation that has my body axis initially oriented like the ECI, if I can obtain this orientation by rotating about this axis of an angle pi. And I think I can, because I take this and it becomes the one that points down, and I take this and it becomes the one that points that way, though. It doesn't seem to be exactly aligned with LVLH. You know what I'm saying?
Yeah.
So I am missing something.
That these are changing in a quite strange way, this vector.
Yeah, it is changing a lot. So this, being distractor, I shouldn't tell you this, but this, as a student myself, will be the time when I take that matrix multiply on top and stick a transpose after that and see what happens. Because maybe we did make a mistake with the matrices.
Here.
Yeah, maybe.
There.
Again, I think we have an error somewhere. We need to debug the error where it is. Because if with the initial conditions that we chose, that are pretty simple to draw in space, we're kind of getting there, or it's kind of making sense, because the axes are along the same lines, but they're not. There are some sign errors. Do we all see that? Yeah, there are some sign errors.
Sign errors.
Sign meaning that if I take, so I'm going to redraw this, okay? And you correct me if you don't think it makes sense. So this would be the ECI, and I put my satellite here, and I said that the velocity is this way, and as a consequence, so this is V0, this is R0, okay, a vector R0, this is X, this is Y, this is Z. Okay. It's a good exercise, by the way. I mean, even if we're struggling to fix it, I think it's good to visualize, one case where quaternions can kind of be visualized. So if we want to go with the LVLH definition that we have done, this orbit is run this way. So the angular momentum is actually, is it going in or out?
Out.
Well, it's going with positive Z, right?
Yeah.
So I made the mistake twice. So, yes. So this is A3, and there's no question about that. But if the angular momentum is pointing up, well, the definition that I gave for LVLH is with A2 going down. So I was right the first time. And then XA1 is pointing this way. Okay. Now I want the quaternion that you are outputting as initial condition for the spacecraft to match this orientation. And we think that that quaternion, Q0, corresponds to a theta of pi over 2 and a, oh, I'm sorry, of pi, right? And an eigenaxis of, what did you say? 0, 0, 1.
0, 0, 1, yeah.
Okay. So this is how my spacecraft should start, with the body axis aligned with A1, 2, and 3. And I should be able to represent that orientation starting from the nominal. The nominal one is basically with the body axis that are aligned. They should be aligned with the inertial one, right? So my struggle here is that no matter what I do, if I rotate these, well, first of all, B3 is up here, so that's a problem. But so if I rotate pi, then my B1 is going to point that way, and that's fine. Then my B2 is going to point the other way here. And so I'm not too happy about this. That's what I'm saying. It doesn't seem it's the right.
Quaternion, quaternion.
Yeah.
But let's check. The problem is a problem.
Does anyone have any comments, input on this?
Yeah, I have a different initial quaternion, but I don't know if it's correct because I obtained the same strange behavior as Marco.
What is your initial quaternion?
So, minus 0.5, minus 0.5, 0.5, 0.5.
Okay, hold on. 0.5.
The first one is minus 0.5. Okay, the second one minus 0.5, and the third and fourth component are 0.5.
Is the norm 1 for this thing?
Yeah, I should check. Just 1 second. Oh.
Non ce la fa più.
So it's some strange angle here.
Yeah, the norm is 1.
Okay. So yeah.
I'm wondering if I made 2 times the transpose operation, because here the DCM is transposed. This DCM goes out, goes out, and it is another time transposed. I don't know if there are 2 transposition. Probably.
I see.
This is not needed more.
Okay. Yeah, I think the more I think about this, if I want to go from my body axis aligned with the inertial basis to something that looks like this, it really shouldn't be. I mean, this, I don't know how I can visualize it. It's going to be some strange angle and some other axis pointing in space. But a quaternion that has multiple components like this kind of sounds more meaningful, because I think basically you can't visualize a rotation that goes from these to these just about one of the coordinate axes. It's probably a more complex rotation if you want to represent it as other axis and then an angle about that axis. So yeah. So what happens when you do that?
I can show the plots. 1 second.
Yeah. Let's run his modified one. See if the
okay. Yeah, perfect.
Yeah. And if we don't solve it here, we can move on to the actual homework too. But I strongly suggest that you guys keep the bugging. And it's really, I mean, there may be other errors, but it's really, I'm sure that it is the problem of making sure that we're using the right DCMs.
Yeah.
So we're not, yeah. Well, you're not feeding the initial Q0 anyways, because you haven't looked at what it is, right?
No, yeah, the Q0 is the old ones.
Yeah. But what is now the initial Q0? I mean, I think you can stop and just look at what it is now.
Mm-hmm.
Mm-hmm. Same.
Yeah, the same one. Yeah. So.
Yeah. It's interesting. Alessia, did you want to share yours?
Yes. Okay.
Could you send me the Simulink model?
To me?
Yeah, yours. Can you send it to me?
Yeah.
Okay, this is what I get.
Yeah. I mean, we see this. They're all pretty ugly.
Yeah.
I don't think it's, yeah. Okay. But you do have a different quaternion. What do you do differently?
I don't know. I use your MATLAB function to transform for the DCM to the quaternion, but with I correct the part in which the quaternion are rearranged. Yes,
yes.
here.
Yes. Huh. Okay.
But maybe there is another error somewhere that I can find.
And what are your moments of inertia?
Yeah, maybe they are just a little different. No, it's the init file. Yeah, this one.
What if you make the middle one very big? The 113.
Yes. I think that the mark has 200 here.
2000.
Okay. So 1, 2, 3. Okay. So let's see what happens. Yeah, maybe I can stop because my simulation period is very high.
What is it doing? Ooh.
No, I stopped the simulation because I've set a very high simulation period. So this is pretty much what happens for one orbit, but it's very, very strange.
Yeah. Yeah, give me some time to look at one of your models. Oh, thank you. You send it to me? Okay. So,
yeah, no problem.
Yeah, I'll look at these and see if I can debug it. So, any other ideas? I'll have to look at what's going on. Sorry that, I introduced this additional thing to do, but I didn't have an actual counterpart to show you. But
Sorry, Professor, just one thing that probably I misunderstood. But why in the for instance in the initialize file, why don't we initialize the attitude in terms of for instance error angles that probably are much more easily to visualize, and then convert them into quaternion according to I think a built-in function which is angle to quat or something like that. But it just to select a proper initial condition. I don't know if it will solve the problem.
yeah, it's another way. Yeah, you can try. You can definitely try. I think if things are done correctly with the DCMs and quaternions, it should work. So, yeah. Give it a try. I can't open your model. I don't know why. That is a problem. It's telling me that you're probably using a newer version of Simulink than I am. Which version do you have for MATLAB? You know?
I was muted. 2020B.
Yeah, I think mine is older.
Yeah, but Marco can generate a Simulink model for an older version because I had the same problem once.
Yeah, can you do it for 2019B? Sorry.
How can I do this?
I think it's in the options when you save.
Save. I share the screen, so maybe Alessia, we can help me.
Okay.
I don't know if it shows up when you do save S. Maybe.
Okay. Save as no. Previous version. Okay.
Yeah.
Previous version. And what version? Which version?
2019B.
Oh.
Hold on. There's several, right? Let me see what I have.
Select MDL. Let's select.
I have 9.7.0, if that makes any sense.
Yeah, no, I think that you have to select the SLX. It's just the format. Yeah.
Okay.
Okay, there's only two options here. Okay.
Okay. And no. Old version. Okay.
You're making me feel old.
Let me know.
Are you using the chat again, or?
Yeah.
Okay. Let's
Just share it.
We can see if this one runs on my computer, and then I guess we can take a short break and move on to something else. If that's okay with everybody.
Better.
Well, I think this is something minor somewhere. I need to find it. And of course, you can keep looking as well, but I want to see if I find it. Here, let's save it here. Try to open that. Let me see if it opens it. Don't complain. And it calls the initialize, right?
Yeah.
Okay. It seems like it opened.
Okay.
And see if it runs.
Yes.
Oof. I need the aerospace toolbox. Gosh. which we do have licenses, but I think they're shared licenses in the university. And so when I have time to look at these, I will have to change those blocks with my own thing, unfortunately.
Okay. Or Alessia, I don't know if you have the version with the not Simulink aerospace Simulink blocks for the conversion, but for the other things
yes.
is quite similar to mine.
Yes, even if we have different results, but I don't know why.
Simulink strange things.
Well, you know, you can't. Debugging during class time is really not. It can be a problem. It can be time consuming. So I think this is a good exercise regardless. And I invite you to continue to clean it up and debug it as I will do. I'll take this one and use my own function to convert the from DCM to quaternion. And
okay.
I'll see if I can find the problem. Okay.
Okay, perfect.
Okay.
All right, so you want to take a quick break and then we look at your initial work on the momentum exchange devices?
Yes.
Okay.
Okay.
Let's be back at, I don't know, in 17 or so.
Okay.
Okay.
See you later.